In this lecture, we're going to continue our study of the transformation properties of forms. And we introduced the idea in the last lecture by showing how this basic one form written in the basis of written in the tensor product basis, right? Written in the basis of the 0-2 tensor product space when the dimension of V equal 2. You could also write that, of course, using our notation for the wedge product, right? These two are the same thing. And when you do this, the transformation rules of the coefficients are different. Of course, this is a one-dimensional vector space, and this is a tensor that lives actually in a four-dimensional vector space, right? It would be 2 to the p, which is 2 to the 2, which is 4. It turns out that particular vector only uses 2 of the 4 basis vectors, so the components of the 0, 0 term, which isn't shown here, is 0, and the component of the 1, 1 term is 0. But once you put it in this form, you're forcing everything to exist in a one-dimensional vector space, a purely one-dimensional vector space of the antisymmetric tensors. The antisymmetric completely, I guess the way to say it is the completely covariant antisymmetric tensors. And we know that all of those differ only by a factor, right? So Q 0, 1, in this case, dx0 wedge dx1, and A 0, 1 dx0 wedge dx1. The only difference is the ratio of Q to A, right? There's some factor that turns Q to A, and that's the only difference. So it's one-dimensional, right? That's because it's a one-dimensional space, right? And we now know that this coefficient here, the coefficient in this one-dimensional space, transforms with the determinant of the covariant transformation matrix. And ultimately, we call that a density. We are saying that this is basically what we call a scalar density. It's a scalar because this thing is a function on the space-time, right? A0, 1. You don't even need the 0, 1 at this point, right? Because there's only one basis vector. So we could just say A is a function on the space-time, and there's only one of them, right? This whole thing, it's only one thing. It's carrying around this weird basis vector, interestingly enough, but it's still just a scalar function now on the space-time, and but unlike a normal scalar function, right, a normal scalar function on the space-time that doesn't carry this thing around, a normal scalar function, when it transforms, it just transforms without without any change, right? The value of that scalar function at x is exactly the same as the value of that scalar function at x prime after you change the coordinates, right? The value should never change because it's a scalar function. In this case, the value does in fact change if you change the coordinates, and it changes by a factor of the determinant of this linear transformation matrix, the covariant linear transformation matrix. And so this actually is it's a unique feature of this kind of scalar, this thing we call a scalar density. And that feature, it scales with this determinant, has to do with the fact that it's a slightly different kind of scalar. And in fact, it turns out this determinant is also related to the orientation of the space. Remember, the determinant of some can be positive or negative, right? And if you did a reflection, if this transformation matrix was simply a reflection on one of the axes, what would happen is you would just push a sign into this object here. And if you pushed a sign into the object here, this determinant just changes sign. And it flips, it flips. And so ultimately, the value of this in the new coordinate system will have a sign change. And that's different than this, right? That's different than this. We'll get to that in a little bit more detail. But the point is this is actually the leading coefficient of a p-form when p equals the dimension of v is actually a different kind of scalar. It's a different kind of scalar than the kinds of scalars we always know. And the reason it's different is that when you change the coordinate system, this scalar here has an actual change that happens to it. This one here does not. And that's why one is called a scalar density and the other is not called a scalar density. So this is what we want to explore a little bit more in this lecture. Is we want to understand it not just for not only do we want to understand this, but we want to understand cases where the dimensionality and p, the dimension of the vector space, and p are different. So let's begin. Let's start by remembering that for any tensor, and I'll just write it down like I1 dot 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 to IP, then J1 dot 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 to JQ, right? This is a regular tensor. Let me clean up my last J here, JQ. That tensor, the component of this tensor, right? So this would of course be D, whoops, not D. This coordinate would be partial I1 tensor product dot 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 tensor product partial IP tensor product DXJ1 dot 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 tensor product DXJP, like that. If this is the tensor Q, right? The Q is, I guess, in what we'd really do is this would be like a bold-face Q, right? That means the tensor, and then this is just some projection of that tensor in a certain basis. And that basis, of course, is defined by the coordinate system, x mu, whatever that coordinate system is. That's how these coordinate basis vectors are defined. If I want to figure out what these components are, what do? I take Q and I operate on the basis vectors, the appropriate basis vectors, and that will tease out the component. So if I operate this on dxi1, dxi2, dot dot dot, down to dxi p, comma, partial j1, dot dot dot, partial jp, like that. Remember, this tensor, it gobbles up p forms, and q vectors, and it spits out a real number. Remember, this is a map that gobbles up p forms and q vectors. Oops, I guess this should be a q, right? Q vectors, and produces a real number. Well, in this case, if you actually put as your forms and vectors to be gobbled up the basis vectors of the two spaces, right? The basis vector I1, I2, I3, just like these up here, you will end up with QI1 IP J1 to JQ. You will end up with the component. And you should be able to see that pretty trivially, right? Because if we literally exercise this, if we literally do it, we would end up with QI1 IP JI1 IP, and then this would be DXI1 partial I1, right? Then I guess some dots, DXIP partial IP, and then it would be DXJ1 partial J1 dot 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 DXJQ partial JQ, right? And then of course all of this equals 1, this equals 1, this equals 1, this equals 1, right? Just like that. And so what the real number that's left, of course, is I1 IP J1 JQ, right? So the component is left over. So this is how you find the component of any tensor in a certain basis. You feed it the appropriate things to generate the component, right? It's that simple. So we're going to do that for one of our forms, right? I'm going to write down a form. I'll call it P, and P is going to be in the strict basis, right? So it'll be I1 less than I2 less than IP. So I pick a series of numbers I'm interested in, right? I'm interested in this particular, well, I need to pick through every conceivable increasing indices structure and sum them all up, but it's going to be, we know what this is, it's going to be PI1 IP, and then it's EI1 wedge wedge EIP, right? I guess what I probably should do, since I'm sticking with the since I'm doing this in the I should do this with dxi1. I should stay in the coordinate basis, dxip, right, like that. So once I've done that, which by the way in shorthand, right, it's p I1 IP with these little lines, dxi1 wedge wedge dxip, kind of like that, right? So these are all the same, right? This is using the sort of the Einstein sum still works even though you've got these little lines here. It just you've got to make sure that you only include the terms where I1 is less than I2 is less than IP. So you're still summing over all those possibilities. Okay, so once you do that, if I want to know so this is P, this is the boldface P. So say I want to know what this thing is in the new basis, right? I just take P, the tensor itself, and I lay down into it the basis vectors that I'm interested in. So I would say delta, say I1 prime, delta I2 prime, delta IP prime, right? So I've stuck into the tensor, this is a tensor, right? It's this form, it's this P form, but it's a tensor. So I stick into the tensor, I put into it, it gobbles up P vectors, right? That's what it does. These things gobble up P vectors. So I put in P vectors. Well, what P vectors am I going to put in? Well, I'm going to put in the basis vectors in the coordinate system I'm interested in. And that, by this definition that we've just studied here, right, that will give me, right, you take Q, you put in the basis vectors, you end up with the component. So I will, once I do this, I will end up with the component in the new, I will end up with I1 prime, IP prime. I will end up with the component in the new basis. So all I've got to do is execute this. But we know how to execute that, right? Because we studied that, I think, 2 lessons ago. We know how to execute the dual space mapping of a form, and this execution is going to equal. What is it going to equal? Well, let's first write it out using this thing here, right? It'll be P I1 to IP dxi1 wedge dxi2 wedge wedge dxip. Sometimes I put two of them here before I go to my dots, and sometimes I leave it out and just do one. There's no rhyme or reason to that. And then this operates on partial I1 prime, partial I2 prime, partial IP prime, right? And when I do that, I should, so look, this is the rule for how you get the components. this here equals p, right? It equals p, so this operating on this should get me p. Now the problem, of course, is that these guys here are in some other basis than these guys here. So the delta function rule doesn't apply. You can't write dxi1 operating on di1 prime equals delta i1 prime. That's not true, right? This is not true anymore. So that beautiful simplification doesn't work. In fact, we need to know how to express each of these in this basis, right? We need to know how to express, we need to know how to express each of these in the di, in the unprimed basis, right? It's going to be some a di plus b di. Well, it's going to actually be. What'll it actually be? Each of these I primes, di prime, is going to equal a del 0 plus b del 1 dot dot dot, where these are the unprimed indices, right? But we can't use this rule anymore, right? But it doesn't matter because we know how this calculation works, and that's all we need. We know how to do this calculation. It's going to equal. I'll just leave it in red because it's kind of important. It's going to equal, let's break out the sum. The sum I1 less than IP of P I1 dot 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 IP, and then it's the determinant, right? It is the determinant of the dual space mapping dxi1. I'm running out of space here. Damn it. I could use this space. It's the determinant of this mapping dxi1 partial I1 prime. And then here would be dxi p partial I1 prime. And then, can I move it any further? Let's see, wait a minute. Let me take this. Let me take this and move it, I'm going to take this, sorry, I got to move this out of the way so I can actually finish this expression because it's kind of an important expression. I'll put it up here like that. Let's see if I can twist it a little bit. Sorry. All right. And then it's dxi1 partial IP prime and dxip partial IP prime, like that. It's this determinant, right? Because each term of the sum, it's this times, let's see, how does it look? Each term of the sum is one term of this, and every time you have this being fed these vectors, you end up with this determinant here, right? We learned that in one of our prior lessons. So this determinant is what dxi1 wedge dot 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 wedge dxip acting on any vector v, w dot dot dot, say z, where there's p of them, right? This whole thing, right, is always going to equal dxi1 v dot 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 dxi1 to z, right, where I fill in all of the other letters in here, all the way down to dxi p to v dot 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 dxi p to z, like that, where you fill in all the letters in the rest of the matrix. That thing, that matrix determinant is always what that answer is. So each term of the sum, you're going to get that determinant in there, right? So, so that is how you calculate any transformation for these Q forms, right? The basic expression looks like this. It looks like Pi1, let's see, let me write this down correctly. Pi1 prime dot IP prime, right? It equals the sum over I1 less than IP of Pi1 to IP, right? Notice these are primes, these are unprimed, so I'm actually sort of removing the Einstein sum here, and I'm just summing over all these ascending sequences times the determinant of that matrix that I just wrote on the other screen, right? And so this is the transformation law. This is the transformation law right here. Now, we immediately see how this applies to the situation we did last time. If the dimension of V equals P, right? If the dimension of V equals P, then there's only one ascending sequence, right? And it goes 1 less than 2 less than 3 dot 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 less than dimension of V. So we'll call this N, right? So that's the only sequence. So this sum only has one term. So P 1, 2 to N equals P, oh, that gets with primes, right? Equals P1, 2 to N times the determinant of, and now it's the full determinant of this thing, right? So what is that determinant? Well, let's write that out one more time. That determinant was dx1 partial 1, like that, all the way to dx1 partial n. And then it's dx, wait a minute, wait, sorry. Yeah. And then it's dxn partial 1 all the way to dxn partial n, right? And so in here, for example, you have dx, say, 3 partial 1, right? And somewhere in here you have, say, dx 3 partial n, and you basically have every one of these things, right? You have every one of these things. But now, when we look at this determinant, well, what is that determinant, right? Oh, I'm sorry, and these are primes, right? These are primes. Shoot, that's really critical, right? These are all primes, because we fed it primes. Jeez, it makes no sense if I don't make that clear, right? So this now, an object like this, dx1, say, partial 2 prime, what that is that is in fact the value of that is the expression of say, well, let's work it out. Let's pretend partial 2 prime equals A partial 1 plus B partial 2 plus dot dot dot, and we'll just say, I don't know, we'll call it J partial N, like that, right? Just a bunch of letters times each of the partials. So this is the differential operator in the prime coordinate system for the second coordinate. It's definitely equal. It's the same vector space, so it's equal to some linear combination of those of those coordinates in the other coordinate system, right? So this is just now dx1, where you substitute this thing here into this slot, right? And that is going to then be 0 for everything except for this first one. So that'll be equal to A, right? That'll be equal to A. And ultimately, that is, if you do it for every single one of these things, what you discover is that this is, in fact, the transformation matrix, right? This is your lambda. This is your lambda. And so you end up with this rule, P1 prime, 2 prime to n prime equals P1, 2 to n determinant of lambda. And that is the, that's the rule we learned in our last lesson for the case where n equaled 2, right? And clearly it's true for any dimensionality when the dimension of V equals P, right? Your maximal form, right? And so you're dealing with actually we call an n form. Usually it's called an n form because capital N is usually the dimensionality of the underlying vector space. So using this rule here, we right away are able to figure out the thing we hinted at the end of the last long lecture. But of course, we can go further. Now, with using this sum, we can say, okay, well, what if I'm at the n minus 1? What if I have an n minus 1 form, right? What about that? So let's have a look at that. So the first thing to think about when we look at that is, well, we're going to look at this thing. Now, the reason this worked out, that it became the transformation matrix, is because we had all n vectors present, right? By looking at an n form, this is a complete n by n square matrix. But generally speaking, this will not be an n by n square matrix. This will be a p by p square matrix, right? And we're going to need one for each collection of increasing indices p. So this is actually the determinant of something less than the total matrix, but it's still a square matrix. It's a p by p square matrix. So it's a p by p minor of this thing, right? And the rows and columns that are in are these rows and columns. So we should actually be able to rewrite this expression by reflecting this thing as the minor of a particular matrix, namely the whole thing. So let's see how we might do that. The notation we used for minor before was something like this. If we had a matrix M, right, a matrix M, and say it was an n by n matrix, we identified a certain minor by putting up, say, I1, I2, dot, 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 to IP, and then J1, J2, dot, 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 to JP. And this would reflect the rows that are included and the columns that are included. And so this was equal to the determinant of the underlying matrix. I guess in this case it was M. So it would be M, I1, J1, dot, 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 to M, I1, JP, and then it would be M, dot, 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 M, I, P, J1, dot, 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 to M, I, P, JP, right? It's the determinant of that matrix. And so the full matrix is n by n, the full matrix M is n by n, but this minor, and you know we're talking about a minor because we start having these weird strings of indices that are straight up and down. So what we're talking about is this determinant. So so when we do this when we use this notation for our transformation, we could say P I1 prime dot 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 to I P prime, right? We could say that equals, let's see, how did we do this? We did this with the sum of I1 less than dot 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 to IP, like that, where I1 and IP are these increasing indices, and then it's P I1 dot 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 IP, and then we have this, our transformation matrix, our covariant transformation matrix, and that's where we throw down, I guess, I1 prime dot 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 IP prime I1 dot 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 IP, like that. And this expression here is simply another way of writing this right here, right? I've just replaced this determinant. I guess, did I write it better somewhere else? Yeah, I guess I wrote it better here, right? This thing here, right, which I put into shorthand right here, but this is the smoothest way of writing it, where we understand that this is the minor, right? And remember, a minor is a determinant. It's not the matrix itself, it's the actual determinant. And so that is the shorthand way of writing this thing. Well, it's not shorthand necessarily. This is sort of the cleaner way of writing things, using the notation we developed, right? We developed this notation in the section on determinants, if I remember right. Now, there was another formula we learned in our determinant section, which I need to write down. And that formula looked like this. It was really interesting, and I told you we needed it because we were going to use it. Now we're going to actually use it. But it's very, well, it's kind of, I would say it's esoteric, but it's very useful. Say the formula would go like this: I1 to IP, and then I guess J1 to JP. Don't let this I and J confuse you, right? When I have primes over here, that could be J, right? As long as I somehow indicated that this was in another coordinate system. I could write P prime J1 to JP's, and then this would indicate, this prime here would indicate that it's in a new coordinate system. So these are just different indices. I could have made them J's, and then this would be J up here. That is purely a matter of how this notation is designed. Wait a minute. Did I get this right? I think these need to be flipped. These need to be flipped. I need to do it this way. This needs to be I1 IP I1 prime I prime P, like that. It needs to be flipped. Sorry, definition is, I got my definition weird. But anyway, this rule, so this esoteric rule I was talking about looks like this. I'm going to write it down in full generality. It goes the I to IP, J to JP minor is actually the determinant of the full matrix M multiplied by the cofactor of the inverse matrix, the cofactor of M inverse, right? The cofactor of M inverse, its minor, J1 to JP I1 to IP. Yeah, so remember that this cofactor, right, it's also a determinant, but it's a determinant multiplied by this another factor that comes from a Levi-Civitas symbol combination. You can go back to the determinant lesson, but it's the cofactor of the minor matrix. In fact, perhaps I should make these brackets parentheses because I'm talking about the inverse. The inverse matrix. You take we're dealing with the determinant. The matrix M is sort of the base matrix. We then take M inverse, and that's a matrix. And then we take the minor described by the flipped combination of these guys. So it's J1 through JP, I1 through IP. We find that minor, right? Well, we want the cofactor of that minor, right? So we got to go through that whole cofactor calculation associated with that particular minor. And then we multiply that by the determinant, and we end up with the minor that we're seeking. So, so this is an expression of how to find the value of a minor. If you know the value of the determinant, and for some reason you find it easier to calculate this particular cofactor, right? So it's a nice expression. But the point is we're dealing with a minor here, so we can take this guy and substitute it in there, and it looks like we'll actually make things harder, right? It looks a little harder, but you end up with this nice determinant, which is a well-known number, and you're swapping out this cofactor. So why would we be interested in doing that? Well, we're going to do that because it's going to help simplify the n-1 calculation that we'll do in a second. But let's first write down the thing simplified in that form. So it'd be I prime 1 to I prime p. That component is going to equal, and I'll just sort of simplify it in advance, the determinant of our transformation matrix times the sum of I1 less than IP. So we're doing all of those strict sums. And then we have the cofactor of the inverse matrix's flipped minor. So that means we get the prime up here. Oh, this is ugly, huh? And then the non-prime down below, like that, times the component in the original basis, or in the unprimed basis. Okay, so this expression here, I guess I'll put a little box around it. That's the same thing as this expression here, right? We're just using this totally cool, very esoteric fact about determinants and minors to make a substitution. Now we consider the n-1 case. So the n-1 case kind of looks like this. P, we still have to do I1 ... I guess I'll call it J ... N, right? Because we do all N, but then there's this one inside, there's this one particular value of an index that we omit, and we put a little hat on it. The hat means it's not included. But otherwise, in order to maintain an increasing list, we know that this has to be, there's only one way to do this, right? It's P1, 2, 3, ... to n, with some number left out. And even if you leave, every time you leave out one number, there's still only one possible increasing list, right? So, we would write that something like 1 ... I omitted ... n. And there's going to be n of these, right? There's going to be, for example, P1, 2 ... up to n-1, where you omit n. Then there's going to be P1, 2 ... n-1 omitted n. Then there's going to go all the way down to P1, 2 omitted ... n. And then there's going to be P2, well, I guess I would go 1 omitted, P1 omitted 2 ... n, right? When I say this actually equals P2, 3, 4, 5, all the way up to n, right? And this one here is actually equal 1, 3, 4, 5 to n, right? And that's the only possible way of doing it. But there's clearly n of these guys, right? And of course there's n basis vectors associated with them, right? This thing is going to be dx2 wedge dx3 ... wedge dxn. and this one, and then this one here will be dx1 wedge dx3 dot 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 dxn, and this one here will be dx1 wedge dx2 dot 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 dxn minus 2 wedge dxn, right? Because here what's missing is n minus 1. And then of course, for completeness, the last one will be dx1 wedge dx2 dot 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 wedge dxn minus 1, and what's missing is dxn, right? That's not there. So there are n of these vectors, right? And that makes sense because we've talked about this already. The n minus 1 exterior power has the same number of the same dimensionality as the first exterior power, right? And this is just an expression of that. Now, of course, there's all these rearrangements. You could take all these rearrangements, but those rearrangements are not linearly independent. They just differ by a factor of plus or minus 1. So this is the basis vectors of this space in the strict basis, and these are the components. So anyway, we can now substitute this concept into here, right? And what are we going to see happen? Well, let's see. Generally, this is going to be one of these guys, right? So there'll be so this will be 1 through n with one of these things missing. This determinant, that's clean. That's always going to be the same, and it's the same determinant that showed up in our n case, right? There's only one determinant of the transformation matrix. So this is a constant number. That'll never change. Then this guy here is some sort of cofactor, right? But the cofactor of, so well, I shouldn't put m in here, right? That m doesn't make sense. That's sort of left over from my definition. What I meant was lambda, right? Lambda, lambda, this is the inverse transformation. It's the contravariant transformation matrix. I didn't do that over here, did I? Let me quickly check. I didn't. No, see, that's the right one, right? Yeah, so I kind of left it, my example was m here, and I let the m wander into this equation. So that's the contravariant transformation matrix. So, but notice that this is also going to be the cofactor of a string of numbers that's just missing one number. So the cofactor of that matrix is going to actually be just a single matrix element, right? If you go back and figure out cofactors, I'm basically dealing with so if I have lambda, if say this is our matrix, if this is our matrix lambda inverse, right, and I have all these matrix elements in here, right? Well, I know that this list of included rows and columns is going to be everything except one, right? So I'm going to include every row and column except one. So all I have to do really is exclude a single row and a single column, and everything else forms the minor of this matrix, and that's what this thing is. But I'm actually interested in the cofactor of that minor. Well, the cofactor of that minor is going to be the single matrix element that is otherwise crossed off, right? Because the cofactor of an n minus 1 minor is going to be a one-dimensional minor, which is just a single element, right? So I can replace this cofactor with a single element of the inverse transformation matrix, right? So that simplifies things a lot, right? And that's going to make this n minus 1 transformation rule pretty simple to apply. So let's apply it in its full generality, and I will go p I1 dot 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 I, and let's go with let's see, I got to pick a letter here that makes sense. Let's try L, and then I'll go IN, but L is omitted, right? L is omitted, and these are primes. These are all primes. And that is by our formula from the last slide. It's the determinant of this covariant transformation matrix, and then I have the sum over all the sequences I1 less than ... I omit, say, k, right? So ... less than in. So this sum here, this sum is now a sum over all these ascending sequences of indices, where basically I'm omitting just one. So we already showed that it's really a sum over this series of indices, right? That's what that is. But I know there's going to be k parts to this sum, just k. There's going to be n parts, right, where I omit each one in turn, for example. Okay, and then that times, let's see, the cofactor of the contravariant matrix, and then I have to put this set of indices up here, and that will be I1 prime ... I prime L omitted ... I n prime, like that, and then I have to put this set of indices down here, right? And I'm just mimicking the formula, right? I'm just going right to this formula and mimicking it. And I will do I1 ... I guess I said k omitted I n, like that. And then over here I put the old matrix element, which is I1 ... I k omitted ... I n, like that. Okay, so now that's my statement, but I have already kind of shown that the cofactor that I've already discussed, that this cofactor is, I can easily simplify it in the case of n minus 1 using sort of this argument, right? The cofactor of an n minus 1 dimensional minor is just going to be a single matrix element. So if I can figure out which single matrix element is, I can get rid of all this and just replace it with one matrix element of, well, I guess one matrix element of this matrix, the contravariant transformation matrix. So that cofactor is going to be the determinant of lambda. Now it's really going to, I'm going to switch this sum to be 1 less than ... k omitted ... less than n. Understand, think about it for a little while and see why this is really the same as that. The subscript i's and I sub 1 and I sub n, those subscripts are there so we can make very, very generalized sequences of indices. Very we want to be able to write almost any kind of index sequence. But the circumstance we're in, there's only one possible index sequence, right? And I've already gone through it. It's this index sequence here, where it's 1 through n. There's really no other choices. So I'm now just sort of installing that in here, because I'm only emitting 1 and I'm demanding an ascending sequence. So I can change this to this. Likewise over here too, right? That's fixed as well. Okay, so I've made that sum. And then, so the cofactor, this cofactor, and you can go back to our thing about our lesson on determinants. But the cofactor is the minor of the complementary matrix, right? So that's the determinant of the complementary matrix multiplied by a factor that's going to be plus or minus 1 depending on a bunch of things. And it's times a generalized Kronecker delta function. But in this case, when you're dealing with a cofactor of a single unit, the generalized Kronecker delta function breaks down into exactly the cofactor we learned in elementary algebra for a matrix minor. And that is going to be minus 1 times k plus L. And it's times the actual matrix element, right? It's the inverse matrix, but it's the matrix element LK, right? That's the complementary. That's the complementary matrix to this minor matrix, and it's the determinant. The determinant of a single matrix element is the matrix element itself, right? That's the determinant of a 1-by-1 matrix. It's the matrix itself. So this, remember, the cofactor is a determinant of a complementary minor matrix multiplied by a certain factor. Well, there's the certain factor. The complement to this thing, to this minor matrix, is this single element, and the determinant of that is just one element. So that was really easy. And then this final value here is P1 K omitted N, like that. So let me just erase this little blue thing here. So this now is our, I guess I should make that 1 L omitted N primes. All these are primes. And this now is our expression for this whole thing. But, so now that's kind of looking a little bit easier, right? This sum has n terms, so it's not a huge, crazy sum. You know, you don't have to go through every permutation. It's just n terms, one at a time. You're picking out every single one of the components in the unprimed system has a role to play, multiplied by some matrix element, and that gives you the components in the prime system. And you need to know the determinant of the matrix to kind of get this formula to work. And by the way, you can, as I just sort of flashed on the screen, you can get rid of this sum over this. I had this sum 1 less than ... and I had k omitted ... n. You can get rid of that and just do it as sum over k equals 1 to n. Because remember, k is just sitting here picking out the matrix element. It's sitting here picking out this, and you omit it from this string here. You don't really need to think of it as the sum over all these sequences. Just think of it as a sum over k. Okay, so what do we do next? Well, first of all, this is kind of the answer to the question, right? The question is, how does this guy, this strict component, when you're dealing with n minus 1, the exterior power of n minus 1, how does it transform when you change bases, right? And if this is the covariant basis matrix of the basis transformation, then this is the answer. This is the answer to that question. This is how and these are strict components, right? These are strict components, and this is how the transformation is done. So in some sense, we've answered the question. But there's a little bit more insight to be drawn here. And let's have a look at that. We can make this a little bit, I don't want to say simpler, but there is an interesting intuition to be had here that we should have a close look at. And it involves a bit of a unobvious maneuver where we multiply both sides by minus 1 to the n minus L. Minus 1 to the n minus L, and then we get this is P1 prime ... L omitted prime n prime. You know what? I just noticed this. There's a prime that belongs on this L here. I'm now putting a prime on that L. There wasn't one there before. Same here. That needs to have a prime, right? These L's are there any other ones? I think those are the only two. Well, here, this one needs a prime. All the L's need a prime because we're dealing with this. This is the index that we're omitting on this side. So the one that's sort of missing over there appears here. It's the same index. It's L prime. But we multiply both sides by minus 1 to the n minus L. Now, one thing that's important is this clever thing we're about to do. A lot of people make the mistake of thinking, oh man, I never could have figured that out. If this was left up to me, I never would have figured out to do this, or I never would have looked at it this way, and I am undeserving of studying this material because it's just so hard for me to grasp. And this is absolutely absurd because it took hundreds of people to figure this stuff out, and they weren't all super geniuses. They all just sort of worked at it, and they worked under some very, look, don't get me wrong, there's geniuses involved in all this history of the development of this subject, but you know, the thing is you don't have to be a genius to understand it. You just have to be persistent, and you certainly don't have to think that you sitting down with a pencil and paper would ever have been expected to create all this stuff from scratch, right? It really did take many geniuses many years to figure this stuff out. And we're just lucky to be learning it, right? There's a prime there on that L. But, so what have I done? I've multiplied both sides by this factor, n minus L, n minus L, L prime, n minus L prime. And then, so that doesn't change anything. But I'm going to combine these two. And the way I'm going to combine them is going to be, of course, minus 1 to the n plus k. But I'm going to write that as minus 1 to the n minus k. They're the same, right? N minus 1 to the n plus k and minus 1 to the n minus k will always be the same. For example, and you could go through the different examples, right? If n is even and if k is odd to maybe m plus 1, you end up with an odd number. But if n is even 2k minus 2m minus 1, well, that's going to be an odd number also, right? Because this difference will always be even. And you know, you can work it out that these two are going to always be the same. And so we're going to change it to n minus k. You know, in other words, we're going to combine them, where the L primes cancel, so you're left with n plus k, and then you just change that plus to a minus arbitrarily because you want it bit symmetrical. There's going to be an n minus an index over here. We're going to want an n minus index over here just for symmetry's sake. So this thing is going to be det lambda sum over k equals 1 to n of, and I'm going to now shuffle things around, the inverse matrix, the L prime k element, and then I'm going to have minus 1 to the n minus k p1 dot 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 k hat dot 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 n, like that. So now I have a new expression, and it doesn't look much different, but I have this thing here that I could combine together, and I could combine together this thing over here. And why might I be inclined to do that? Well, I'm going to call this, I'll put it in green, I'm going to call this thing, oops, not R, P, but I'm going to put the K, I'm going to make it just a single index K, right? Because if you think about this, this really only depends on this number K. We know that it's going to go from 1 to n with K omitted. So all I really need to know is K. But notice I'm going to put this K, why do I have a prime? There's no prime there, no prime, no prime. But you'll notice I'm putting this K in the contravariant position. And that's sort of the really interesting trick here. I'm going to put that in the contravariant position. It absorbs this factor, and I put this in the contravariant position. And then this K is going to sum over this K. And that sum is perfectly logical, because this summation here forces this sum on the K here and here anyway. So you're actually summing over the K both in the down position here anyway, right? Because that's what this summation sign says. But so I can now exploit the Einstein summation convention by putting the K upstairs, right? And getting rid of that sum. So I'm now going to write this as det lambda minus 1 to the L prime K P. Why do I keep making that P and R? P K. And on the other side, I'm going to call this thing P L prime. Right? This thing here, I'm going to call that P L prime. And now have a look at this thing. This red boxed equation, this thing is really interesting. If this was the component of a 1, 0, of a 1, 0 tensor, right, then it would transform that way without that determinant, right? In other words, this is the law of the transformation of a 1, 0 tensor component, right? The component is contravariant for a 1, 0 tensor. And that would be that transforms like the component, right? The K sums and you get the L prime. There's the contravariant transformation matrix. And so that is the contravariant transformation of this with the lambda being the covariant matrix. Like lambda is the covariant matrix, lambda inverse is the contravariant matrix, and the 1, 0 tensor component uses that to transform. The difference is that, wait a minute, the difference is that we have this thing in there, right? Right back where it belongs. Belongs right there. That makes a lot of the difference in the world. It's very close to transforming like a 1, 0 tensor, but it's got this guy stuck in there. It's got this guy. And this rule is the rule of transformation of a 1, 0 tensor density. This is a different transformation rule. When you see the transformation rule of a 1, 0 tensor, but you've got this thing in there also, then we call it a 1, 0 tensor density. All right, and we'll talk about the general notion of a tensor density in a moment. But I want to show you how we got there. We got there through the straight-up calculation of the transformation of the strict basis components, which was this. That was the answer to that question. But we can also push on a little more and realize that these things here transform in a way that's very close to a 1, 0 tensor density. The difference being this factor here, these factors in front, this n minus L and the n minus K. So this pk has this sign factor. Now, in many treatments, what they'll do is they will assign this sign factor not to these components, but to the basis vectors themselves. And what they'll say is that the set of basis vectors is dx1 dx m omitted and these are all wedged, right? Wedged together. Wedge dxn. Oops. That whole thing multiplied by minus 1 to the n minus m, like that, right? And then the sign gets absorbed in the basis. So this is the basis set, right? So frequently they'll absorb it there, right? And once you've done that and you've decided to change the sign of the basis set, then when you go back here, turns out you don't need the factor here, and this transformation doesn't require the definition of this to absorb these weird sign changes. But the point is that in the n minus 1 exterior power, this is how these things transform, and they actually transform like 1, 0 tensor densities, especially if you define the basis set this way, with this factor in it. Okay, so that is that's how we handle we've done a demonstration for lambda n minus 1, so next time we'll do it for lambda n minus p in general. Unfortunately, when you do this in all generality, you can still always make a maneuver like this, right? But the result doesn't always end up being a density of some kind. There's something a little more exotic here. There's a minor matrix here that this becomes more and more complicated. Right now, it's a simple matrix element itself, or a sum over matrix elements, so it's nice and easy. But if once we go to cases like this that are beyond n minus 1, this thing becomes more complicated and it isn't so easy to describe. However, you can always get a nice smooth little formula. It's just not going to be this clean form of a tensor density. Okay, that's all for this time, and we'll keep going next time.